All right, so last time we started talking about the binomial distribution, and it has four conditions that must be met in order for it to be not just a discrete distribution, but a binomial distribution, a special type. So the first one was your experiments, you have to have a fixed number of trials of your experiment. So you have to have a set number of times you're going to run the experiment. Number two, those trials have to be independent from each other. So what happens in the first trial can't affect the probability of what's going to happen in the second trial or any of the other trials, and vice versa. And three, every trial must have only two outcomes. That's where it gets the name binomial. So only two outcomes per trial, and we call them success and failure. So if we're going to count the number of times a coin lands on heads, we're going to call heads success, we're going to call tails failure. But the important thing is we just have two outcomes. And the last one is we want the probability of that success to be the same every time. So we're doing the same experiment every trial. And another kind of exception that we made was if you don't have independence, but your sample size is less than 5% of the population size, you can go ahead and assume you have independence because the probabilities aren't going to be that much different when you take each time you pick from your population and you take that individual out, it doesn't change the probability that much on the next pick. So that was how do you determine if your distribution is binomial. All right, so I want to go back to a problem. We did one similar. It had multiple choice questions in it. So let's say that there are 5 questions and we have answers A through D. And we're going to randomly guess on these. And we did things like, what's the probability that we get all the questions correct, all the questions incorrect, at least one correct, okay? We never did any where we kind of mixed them up. So let's find the probability that we get exactly 3 correct. How many did we get incorrect? 2. So that's kind of added on, right? So 3 correct and 2 not correct. Okay, out of 5. All right, so if we use our old ways, we could say, well, the probability we get the first one correct is 1/4, right? Because there's 4 answer choices, A through D. Probability we get the second one correct is 1/4. The third one correct is 1/4. The probability we get the fourth one incorrect is 3/4. And the probability we get the last one incorrect is 3/4, right? So if we multiply all that out, we will get the probability that we get the first 3 correct and the last 2 incorrect. But that's not all, right? That's just one way to get 3 correct and 2 incorrect. So we would also have to compute the probability, let's say we get the first, third, and last one correct, and the second and fourth one we get incorrect. So that's also 3 correct and 2 incorrect, right? So we would have to multiply all that out and get that probability. And are there other ways? Yeah. So using the old method here, we would have to figure out all the different ways we could get 3 correct and 2 incorrect and multiply all that out and add all those probabilities together, and it would be very tedious, right? So we have a better way. This is actually a binomial experiment. Okay, we have 5 questions, so fixed number of trials. Success is getting it correct. Failure is getting it incorrect. The probability is the same every time of getting it correct if we're just guessing, right? And the trials are independent, so this is binomial. So I'm going to show you how we have a formula for computing binomial probabilities, and it makes things easier. The formula is a little bit hard, so that's why we're going to go over this and explain why it is the way it is. So if you look at these two, they're almost the same thing, right? In fact, they're exactly the same, because we're multiplying the same things together, and it doesn't matter what order you multiply in. You know, put it up here. 2 times 3 is 6, and 3 times 2 is also 6, right? They're the same thing. It doesn't matter what order they're multiplied in. So these are you're multiplying the exact same things here. And every different way to get 3 correct and 2 incorrect, you're going to get the same thing on all of them. So part of our calculation here is going to be, well, I know I'm going to be multiplying 1/4 3 times. And I know I'm going to be multiplying 3/4 twice. So that's going to be in all those calculations. I just need to know how many ways, how many of these, that's one way, that's 2 ways. I need to know how many ways total, and then I'll just multiply by that number. Okay? So what this boils down to it's like the, remember we did the different ways you can order genders, right? Instead of gender, instead of boy, girl, it's going to be you got the question correct or you got the question incorrect. So that first thing is I got the first 3 correct and the last 2 incorrect, right? And I want to know how many ways I can switch those around, right? So another way is this one. So that's the second way. So what I need is how many ways I can reorder those. Well, that's, there's 5 of them, so that's 5 factorial, right? But some of them are identical. So if I switch those 2 C's, it's the same thing, right? So I'm going to divide by the identical items. So there are 3 C's, there are 2 I's, so I divide by that. So I'm recording the screen. I didn't record this, so I need to go back and write it down. So I'm going to write it down on the board here. That's one way. Here's another way. There are 5 of them, but some of them are identical. So there are 3 C's and 2 I's. Right. Well, that looks similar to something else we did too, right? So what if we did 5C3? The formula, that's 5 factorial over 3 factorial and then 5 minus 3 factorial. Right? So that's 5 factorial over 3 factorial, 2 factorial. It's exactly the same thing. That's kind of weird, but it is. Okay. So the total number of ways I can choose which 3 questions I'm going to get correct out of 5 is 5C3. Okay. So let's see what that is. So that's 10, right? So there are 10 ways. So if we did it the old way, we'd have to multiply all that out 10 times and then add all those together if we didn't understand that they were the same, right? But instead, I'm just going to multiply this by 10, right? Because all of them have a 1/4 3 times, and all of them have a 3/4 twice. So I'm just going to multiply this by 10. That'll get them all done for me, right? So let's see what that is. So 10, I'm going to use 0.25 for 1/4. I'm going to use 0.75 for 3/4. So I get 0.0879. 0.0879. So the great thing about, why we like the binomial is all the probabilities in a binomial distribution work the same way. Okay, so we actually have a formula that will calculate this probability for any situation that's binomial. Okay, so 0.0879, let me just write that down. So here's the formula. It looks kind of big and scary, but I think once you understand how it works, it's not that big of a deal. Okay. So in the formula, it's got all these symbols, and here are what all the symbols mean. So the P is the probability of success in each trial. Remember, that's got to be the same every time. In our case, the probability of getting each question correct was 1/4. It was 1/4 for every question. So that means P is 1/4. 1 minus P is the probability of failure, right? Because those are complements. 1 minus 1/4 is 3/4. Or 1 minus 0.25 is 0.75. That's probably getting the question wrong. N is how many times we're going to run the experiment. In our case, it was 5. We answered 5 questions randomly. And X is how many times we're going to succeed. In our problem, we wanted the probability of getting 3 questions correct. So X in this is 3. So we first multiply by how many ways this thing can happen. That's NCX. That's, in our case, that was 5C3. Times the probability of success, or 1/4 in our problem, raised to the number of times we succeeded, 3. So it was 1/4 cubed. And then 1 minus P is the probability of failing each time. And then we raise it to the N minus X. So if there are a total of 5 trials and we succeeded 3 times, this is how many times you fail, right? N minus X. So this was 3/4 squared. That N minus X is how many times you fail if you succeed X number of times, and there are N number of trials total. Right, so let's do another example, and let's see if we can we're just going to plug it into the formula and see what happens. So it says, use the formula to find the probability of having exactly 3 girls in a family of 4 children if the probability of that child is a girl is 0.53. So instead of it being 0.5, we're going to say we're slightly more likely to have a girl. So make that bigger. N is the number of trials. So you tell me what N is. 4 children. P is the probability of getting a girl every time. So that's the probability of success. Again, we're saying girl is success, boy is failure. But if we were counting the number of boys, we would call boy success and girls failure. Okay, so it's just a term that we use, right? So 1 minus p is probability that we fail. In this case, this is probably we have a boy. So that would have to be 1 minus 0.53. And then x is number of successes. So in this problem, we want the probability of getting 3 girls. So that would be 3. And n minus x is how many failures we have. So if we have 3 girls out of 4, then it means we had 1 boy. So that would be 1. So, if you're going to use a formula, you're going to, and any time you do this, you're going to write down all these things. You're just going to go through the problem and write down, you need n, p, and x at the very least. And then you can figure out 1 minus p and n minus x pretty easily. You might not have to write those down, but you need to write down at least these, just try to figure it out from the problem. So the probability of number of successes is 3, is NCX, so that'd be 4C3. P raised to the x, so we're going to have 3 girls, so we're going to be multiplying 0.53 3 times. And 1 minus p to the n minus x. So we're going to multiply 0.47 once because we had 1 boy. So let's see what this is. So 0.2799. So I need you to get StatCrunch open. From now on, we need StatCrunch in every class, okay, just about. So that should be the first thing you do when you get to class. Log in and get that StatCrunch open. Because StatCrunch will compute this for you. So you just need a blank sheet open, a blank spreadsheet. Does anyone need the attendance? All right, do you remember where the custom calculator is? So you're going to go to Stat Calculators. The binomial distribution is a special one with a special name. So it's got its own calculator. So you go to Stat Calculators and you click on binomial. So let's do that first problem we did with the questions. So there were 5 questions. So I'm going to make n equal to 5. The probability of success was the probability of getting a question correct. That was 1/4. You can't type 1/4 in. So you have to type in the decimal. So it's 0.25. 1 divided by 4 is 0.25. And we wanted the probability of getting exactly 3 questions correct. And it tells us 0.0879. Is that what we got earlier? Yeah. So it calculates that for you. If I wanted to know, what's the probability that I get less than 3 correct answers? Less than 3 correct. That means 0 or 1 or 2 correct answers. I would have to compute that binomial formula 3 times and add those together. Instead, with this calculator, I can just put in less than 3. I can change the equals to less than, and see it highlights 0, 1, and 2 that in red. That means it's calculating those together and adding them up. So it's very, very nice calculator. So it'll help. It'll help you do the homework, and you're allowed to use it on the tests. Let's do the problem we just did with the 3 girls out of 4. So there were 4 children. The probability of getting a girl was 0.53. We want to know the probability of getting exactly 3 girls. So 0.2799. That's what we got. Okay. So that's stat calculator's binomial. Okay. I have no problem with you using that calculator. But you still got to know that it's a binomial problem, and you got to be able to plug these things in correctly and compute the correct thing. StatGrunch just takes care of the tedious calculations. All right, so keep that open. We're going to do the next problem together. I'm going to change some of these too because I don't like the numbers here. But it says in a region, 80% of the population have brown eyes. If 20 people are randomly selected, find the probability that exactly. Let's change this to 18 instead of 8. I don't like 18. I don't like 8. Let's make it 18. Let's make that 17. Let's make this 15. Let's make that 14. Let's first check and see, is this a binomial? So, are there a fixed number of trials? Yeah, we're going to pick 20 people. Okay. Are there 2 outcomes in every trial? Yes, so they either have brown eyes or they don't. So that's 2. Are the trials independent? They are not. But we can assume that 20 people is going to be less than 5% of the population. Right? So, it says in a region, what is 25% of? If you divide 20 by 5%, that'll tell you 400 people. So as long as our region has more than 400 people, then we're okay to assume independence. Okay? Because when we take one person out of the pool, it doesn't change the probability that much. I would assume a region has more than 400 people. Do we agree? I think so, right? in a region, we're not talking about a small town or a classroom or something like that. It says in a region. I'm assuming more than one city, okay, in a region. So based on that assumption, we can assume independence here. And that means we can use 80% as our probability every trial, okay? Because it's really going to be close to 80% every time anyway. Even if we don't assume independence, it's going to be close. Okay. All right, so we're going to use the binomial anyway. So in the calculator, I'm going to put in 20 for n. The probability of picking someone with brown eyes is 80%, so I'm going to put in 0.8 as the probability. And I want to know the probability that exactly 18 have brown eyes, so I'm going to put in equals 18, and I get 0.1369. Well, it's probably that at most 17 have brown eyes. What does at most mean? What symbol am I going to use here? Less than or equal to, right. The biggest it could be is 17, but it could be anything less. That's at most 17. So I'm going to change the symbol here to less than or equal to. And you can see what it highlights. The highlighting should help you. I got to change 18 to 17 too, right? I didn't do that. So I caught my mistake there because it highlighted 18 and I knew that was wrong. So look at what it highlights and make sure that that's the actual thing you're trying to calculate. So less than or equal to 17, so that's 0.7939. What about at least 15? What am I going to write here? What's the symbol in between? At least greater than or equal to, right? The least it could be is 15, and it could be anything bigger. So that's greater than or equal to 15. So I'm going to change my symbol to greater than or equal to, and then 15. 0.8042. Right, between 10 and 15. So this is probably that X is between 10 and 15. We're going to assume that it's inclusive. So again, this calculator is very nice. It has a between option at the top. So you click this button at the top, between, and it'll let you type these in. I did that wrong. 10, from 10 to 15. And again, it highlights in red what you're calculating, so that'll help you decide if you've done it correctly. So 0.3698. E says, would it be unusual to select 20 people from this population and get fewer than 14 of them that have brown eyes? So fewer than 14, what's the symbol? Less than, right. So I need this probability to determine if it's unusual. So just less than 14. So I'm going to switch back to standard. Change my symbol to less than, do less than 14.0867. So is that unusual? No. So the answer is no, because the probability is not rare enough. It's not less than 5% or 0.05. Everybody good? So 2 says an airline has a policy of booking as many as 25 people on an airplane that can seat only 24. Past studies have shown that 92% of booked passengers actually arrive for the flight. Find the probability that if the airline books 25 people, not enough seats will be available. So, how many people would have to show up in order for not enough seats to be available? All of them, right. So this is the probability that x equals 25. So in the calculator, n is 25. The probability that each passenger shows up is 0.92. That's p. And I want the probability that the number of successes is all of them. So 0.1244, or 12%. If they're all the same, there's only one combination that can happen, right? So this would be 25C25 is 1. So, if they're all the same, you don't have to use this formula. I could have just said 0.92 multiply it 25 times, and I get the same answer. It's when there's a mixture between different ones where this binomial helps. It helps a lot. It helps a lot in doing these calculations, so we don't have to figure out all the different ways things can happen. The binomial figures that out. Any questions? All right, so this exercise here wants us to look at the distributions. So it says open the binomial calculator. I want you to do this with me. I want you to type in p equals 0.2, x equals 10. It doesn't really matter. And we're going to start with n equals 10. And we're going to look at the shape. So we don't care about the probability. We just want the shape of the distribution. So this is the binomial distribution when n is 10, p is 0.2. Okay. So what's the shape? Skew to the right. Right, let's change n to 50. It's still a little bit skewed to the right, but it's not as bad, right? It's not as skewed. Okay. What about n equals 100? That's n equals 100. And then n equals 1,000. So as n got bigger, what happened to the distribution? It went from skewed to bell-shaped, right? The higher n is, the more bell-shaped, or the closer it will get to a perfect normal distribution, right? So as n increases, the binomial distribution becomes more bell-shaped, or you could say normal. In fact, we have a rule for this. If n times p times 1 minus p is at least 10, then you can use the normal distribution in place of the binomial or vice versa, whichever one you need. They're going to be close enough together that you could use either one. Okay. So we'll say this. If this is true, then the binomial is really close to the normal distribution. And if you make n go up more, then it'll get closer, it'll get even closer, you know. But as long as this calculation is at least 10, then you have a pretty good approximation of the normal distribution too. Okay. So let's say we flip a coin 100 times, and we're going to count how many times we get heads, right? Is that binomial? Yeah, it's binomial. How many heads do you expect to get? If the probability is 0.5 for getting heads, right, or 1/2, and you flip a coin 100 times, how many times do you expect to get heads? 50 times, right? Well, that's the expected value of the number of heads. And all I did, right, was multiply 100 times 0.5. This makes, if you have a binomial distribution, you can find the mean really, really easily. You just multiply n times p. That's all you have to do. If 80% of people have brown eyes, and you're going to pick 20 of them, you would expect 80% of your 20 to have brown eyes. Does that make sense? Yeah. So you multiply 80% times 20, multiply 0.8 times 20, you get 16. You would expect 16 out of 20 to have brown eyes. So the mean of a binomial distribution is just n times p if it's binomial. It's so easy that StatCrunch does not calculate it for you. Okay, you can't do this with StatCrunch. There's not a mean binomial function. You know, when on this distribution, you know, the custom calculator gives you the mean and standard deviation. This binomial calculator does not. You know, there's no mean anywhere in here. Okay, so it's just n times p. So you have to remember that. If it's binomial, the mean is n times p, and the variance is n times p times 1 minus p. That was in our rule that we just said, right? So the rule says if the variance of the binomial is at least 10, then it's very close to normal. And then if you take the square root of it, you get the standard deviation. And if we know these, we can do the range rule of thumb. Remember the range rule of thumb? 2 standard deviations from the mean. We can do z-scores for binomials. So we can do all that stuff that we know how to do if we have the mean and standard deviation with a binomial, and it's really easy because the calculations are pretty easy. So I'll tell you that on tests, computing the mean and standard deviation of a binomial is missed a lot. It's one of the most missed problems, and it is the easiest calculation that we do. The reason is that StatCrunch doesn't do it. Okay, so you just have to remember you can look through StatCrunch. It's not gonna help you. Okay. The only way to do it in StatCrunch is with that. You have to do the calculator, right, the compute expression calculator, but you might as well just use a regular calculator to do that. Or you can come up with the entire distribution table and throw that into the custom calculator, and that would be way too much work. Okay, it's much easier just to multiply n times p. Okay. So I'm going to project this because we don't need StatCrunch here. So this says Clarinex D is a medication whose purpose is to reduce the symptoms associated with a variety of allergies. In clinical trials of Clarinex D, 5% of patients in the study experienced insomnia as a side effect. If 240 users of Clarinex D are randomly selected, how many would we expect to experience insomnia as a side effect? We would expect 5% of the 240. So this is asking for the expected value, which is the mean. So it's just n times p. N is 240. And this is the probability we pick somebody who had this side effect of insomnia. So 5% of 240. I think that makes complete sense. If it doesn't, you need to think about it or come ask me about it and I'll try to explain it. So we would expect 12 people out of the 240 to have insomnia. Would it be unusual to observe 20 patients experiencing insomnia? So would 20 be way too high? Would it be unusually high? Okay. Well, we could do a bunch of things. Let's compute mu plus 2 sigma. That would be 2 standard deviations above the mean, right? So I need sigma, so I'm going to do my sigma calculation here. It's the square root of n p and 1 minus p so that's sigma. The square root of n times p times 1 minus p. So 1 minus 5% would be 95%. 100% minus 5%. So let's do square root 240, 0.05, 0.95. And let's round it. How about 2 decimals? Probably shouldn't round it, but I'm going to round it here. So the standard deviation is 3.38. Well, what's 2 standard deviations above the mean? That would be an unusual result if we got something 2 standard deviations above the mean. So that would be 12 plus 2 times 3.38. 12 is the mean, that's the expected value. And 3.38 is the standard deviation. So 12 plus 2 times 3.38. 18.76. So 18.76, anything above that we would say is unusual. So would it be unusual to observe 20 with insomnia? We're going to say yes. Since 20 is greater than 2 standard deviations above the mean. The other thing we could have done was find the z-score. You remember the z-score? So we would take 20, we would subtract the mean and divide by the standard deviation. And the z-score is 2.37. So that tells us that 20 is 2.37 standard deviations above the mean, which makes it unusual, right? Anything above 2 or less than -2 is unusual because it's more than 2 standard deviations away from the mean. Anything between -2 and 2 is called usual, right? That was from a long time ago, but we still need to remember that. We're going to keep using that. Okay. So that's pretty easy to find the mean. I want you to answer this question. And use StatCrunch if you want. Or you can use the formula. I'm going to go ahead and export my